So what we are going to look at today is another type of function, this time called a reciprocal function. So a reciprocal function is just taking the reciprocal of a given function. So if I have a function f of x, such as x squared minus 5, the reciprocal function would be 1 over f of x, or 1 over x squared minus 5. So it takes whatever your function is, and it takes the reciprocal of that function. So it says, exploring a reciprocal function. Consider the function f of x with the equation y equals x plus 3. If we write the equation of the reciprocal function, what would we get? What would the reciprocal function look like? It would be 1 over x plus 3. Okay? So the graphs of y equals f of x and the graph of y equals 1 over f of x and a partial table of values is shown together. What I would like you to do is I would like you to spend the next couple of minutes answering the questions or filling in the blanks of these 4 bullets. So determining or stating what the y-intercept, the x-intercepts, etc. Okay, what is the y-intercept of my function f of x?
3.
3. Okay. What is the y-intercept of the reciprocal function? 1/3. Because it would be the reciprocal of the original. What is the x-intercept of this function? -3. And there is no x-intercept in the reciprocal. But what I have is I have a vertical asymptote. And I'm not sure if we haven't talked about asymptotes. Asymptotes are this imaginary line. I don't know if you've seen, there's t-shirts that have like Gandalf coming up to an asymptote and thou shalt not pass. It's because an asymptote is a line that you can come up to as close as possible, but you can't actually cross over the line. So the other example I use, and that's the magnet that I made, what part of an inverse tangent function do you not, or approaching an asymptote, do you not understand? It's from the Big Bang Theory. When Sheldon's wall climbing, he looks down and realizes how high he is off the ground, and he won't move. And he says, I feel like an inverse tangent function approaching an asymptote, to which Barry's like, huh? And Sheldon's like, what part of this don't you understand? Well, it's because he can't go up because there's an asymptote. And he can't go down because there's another asymptote. So it's Sheldon's way of saying, I'm stuck, I can't go up, and I'm too scared to go down. It's approaching an asymptote. So in this question, does it look like there's an asymptote, that there's this pretend line that the graph comes up to but doesn't cross over? Where is that line? At -3. So what we can do is we can draw that in with a dotted line. So some of you, when you were graphing some of these questions, you would get this line, the graph would draw this line, and then there would be this like harsh straight line that would move up, and then it would draw this one nicely. Well, some of the calculators draw in the asymptote. But the asymptote is not really part of the graph. It's there, but it's not there, so that's why we put it in with a dotted line. So the equation of this asymptote is that x equals -3. So the relationship is the x-intercept becomes the asymptote of the reciprocal. Why is this an asymptote? Well, if I put -3 into this equation, what do I get? 0. And can I divide by 0? No. So this point here doesn't exist on the graph. That's what creates the asymptote. It's that part of the graph that it can't be. Okay? Then there's 2 points on the graph which appear both on f of x and 1 over f of x. So the same input gives me the same output. Where were those 2 points? So look at the table of values this time. Where do you see the same values in a row? At -4 and at -2. So the values of those points are -4 and -1, and -2 and +1. So what that means is that when f of -4 equals -1, so then the reciprocal of that is the reciprocal of this number, which is 1 over -1, which equals -1. That's how it creates, or that's why it becomes an invariant point, because when I take the reciprocal of -1, I get -1. When I take the reciprocal of +1, I get +1. Whereas everything else, the reciprocal of 2, 1/2, 3, 1/3, 4, 1/4, -2, -1/2. So the reciprocal stays the same in these 2 points. So we call them invariant because they don't vary. They stay the same. The other thing that you might notice about this graph is, in addition to this vertical asymptote, there's also a horizontal asymptote. Where's the horizontal asymptote? At 0. It's the x-axis, which as an equation would be y equals 0. So if we complete the following at the bottom of the page, it says, when f of x equals 0, so when the original graph is equal to 0, the reciprocal graph is going to have this vertical asymptote. And then as the original graph approaches positive infinity, so as this number gets higher and higher and higher, the result, so as my x values increase, my y values are increasing in my original graph. As my x values increase, what are happening to my y values in this graph? Are they getting bigger or smaller? My y values? My y values are getting smaller. So they're approaching 0. If I look at this side, as my as my x values get smaller and smaller, -10, -20, -30, my y values are getting smaller as well. But in this graph, as my x values are getting smaller, my y values are getting closer to what number? 0 again. So as the f of x approaches positive or negative infinity, the graph of 1 over f of x gets closer to a horizontal asymptote. And again, the reason for that has to do with the idea of the reciprocals. If I have a y value here that is like -20, the reciprocal is going to be 1 over -20, or -1/20, which is a small number. If I have a number that's like 1,000, the reciprocal is going to be 1/1000. Again, an incredibly small number getting closer to 0. Okay, so let's look at the next page with a quadratic. If we consider the equation x squared minus 4, what would the reciprocal function look like? So y equals 1 over x squared minus 4. So on this page, we have both graphs. The lighter colored one is my original x squared minus 4, and the black one is the reciprocal 1 over x squared minus 4. So if we look at the table of values, again, when x equals -4, the original equation is 12, the reciprocal is 1/12. 5, 1/5. -3, -1/3, and on. When x equals -2, the original function is 0, and the reciprocal is undefined because the reciprocal would be 1 over 0, which I can't have. And then the same thing happens when x is equal to +2. Okay, so then again down here, when x is equal to 2, f of x is equal to 0, and the reciprocal would be undefined because I can't have 1 divided by 0. So if I look at this graph that's in the light gray, where does it cross the y-axis? -4. And the reciprocal function then would cross the y-axis at -1/4. The reciprocal being the reciprocal of -4. So I'd have -1/4. And that's right here on the table of values. When x equals 0, what does the value of y equal? What are the x-intercepts of my graph that's in gray? -2 and 2. And in the reciprocal function, I get these vertical asymptotes again. I get these imaginary lines, which we can draw in as a dotted line. And this is what those dotted lines look like. And those dotted lines also go through the points of +2 and -2. So the equations of the asymptotes are x equals 2 and x equals -2. And then I have a horizontal asymptote right here. So the graph comes close to the x-axis but does not cross over the x-axis. So the equation of that would be that y equals 0. So it says in the first example, we were able to determine the invariant points of the graphs of f of x and 1 over f of x by using the table of values. What we did is we looked on the table of values to see where we had the same outputs. Okay? When we try to do that for this one, we don't have anything that is the same. But it doesn't mean that there aren't invariant points. Invariant points would still actually exist. Explain why we could use the line y equals a positive and a -1 to find the invariant points of these two graphs. So what that means is if I have y equals 1 and I graph that, so I'm going to draw the line y equals 1. So this is my line y equals 1. If you notice, there's 2 points on the graph where this line intersects both of these. That's right here and right here. What that means is that when y is equal to 1, f of x is equal to 1. When y is equal to 1, 1 over f of x is also equal to 1. So that's where I can use this line. The reason I can use this line is if y equals f of x equals 1, the reciprocal would be 1 over 1, which then equals 1. And I can do the exact same thing when f of x equals -1. The reciprocal would be 1 over -1, which equals -1. So I could draw that line as well. And there's my y equals -1. And then I have 2 more invariant points, right here and right here. It's just in this circumstance, the x values are not whole numbers. They're going to be possibly irrational numbers that would give me those invariant points. And finally, When f of x equals, so when f of x is equal to what value? The graph of 1 over f of x has vertical asymptotes. So where does the graph have vertical asymptotes? What are these values here? -2 and 2. So when the original graph was equal to -2 and 2, the reciprocal graph has asymptotes. Okay. Then, as f of x approaches blank, the graph of the reciprocal approaches closer to the horizontal asymptote. So when does this go to the horizontal asymptote? It goes when my x values get to be incredibly small, so to -infinity, or incredibly large, to +infinity. So the way that I can write that is as f of x approaches both positive and -infinity, the graph approaches closer to the horizontal asymptote that has an equation of y equals 0. Okay, so we're going to look at the properties. So if I look at the properties of reciprocal equations, reciprocal functions, when f of x is equal to 0, the reciprocal function would have what? Because the reciprocal function would now be 1 over 0. Vertical asymptote. When the original function is positive, the reciprocal function would be, so in other words, if f of x equals 4, what does 1 over f of x equal? 1 over 4, which is positive. So when the original function is positive, the reciprocal would also be positive. When the original function is negative, the reciprocal would be negative as well. When the original function is equal to 1, the reciprocal would be equal to 1 as well. And when the original function equals -1, the reciprocal would equal -1. And this is what we call our invariant points. When the original function increases over an interval, so f of x goes from 5 to 7 to 8 to 9, etc., the reciprocal function would do what? It would decrease, because I'd have 1/5, 1/7, 1/8, 1/9. Those are all smaller numbers, so it would decrease. When the original function decreases, so I go from 4 to 2 to 1 to 1/2 to 1/3, the reciprocal would do what? It would increase, because that 1/2 would become 2, 1/3 would become 3, 1/4 would become 4. So I would have an increase in the same interval. When the original function approaches 0, the reciprocal approaches positive or negative infinity, which is the question. So if f of x equals 1/10, the reciprocal is 10. If f of x equals 1/100th, the reciprocal would be 1,000. So that's where it goes, it gets bigger and bigger. And the graph would then approach the vertical asymptote. And I'll show you that on the graph. When the original function gets closer and closer to positive or negative infinity, the reciprocal gets very, very small. So it approaches 0, and the graph gets closer to the horizontal asymptote. So I'll just show you that again on the previous page with that quadratic. In this right here, so this part of the graph right here corresponds to this section in here. So this value here might be like 4/3, or sorry, not 4/3. I'm looking at this backwards. So as the graph approaches 0, the reciprocal gets higher. So this value right here, which might be like a 10th, the reciprocal is 10. If I get to be 100th, the reciprocal is going to be 1,000, and it gets closer to this asymptote. When I go the other way, and these values get larger and larger, the reciprocal gets smaller and smaller, and it approaches this horizontal asymptote. Okay? So the one thing that you're going to be asked to do is you're going to be asked to sketch the graph of a reciprocal function. And you may not actually be given the equation of the original. If you're given the equation of the original, there's a lot of strategies that you can use to sketch the reciprocal. You could use your graphing calculator and type it in as 1 over whatever that equation was. You could put it into a table of values and calculate all the points and sketch the points out. But if all you were given was a graph and said, find the reciprocal of this graph, there's characteristics that we need to remember. And that's what this goes through. The zeros, which are the x-intercepts, you want to write that in as a reminder. The x-intercepts of the original function become my vertical asymptotes. So I draw them in first. Okay? Then I mark my invariant points. So I look at that graph. So if my graph kind of goes something like that, and this is where y equals 1, I mark this invariant point because it's going to be a marker on my new graph. If this was y equals -1, I would mark these 3 points on the graph so that I could find them when I draw my new graph, because they're going to be the same on both of those graphs. That's what makes them an invariant point. Okay? The y-intercept of the reciprocal, the y-intercept of the reciprocal graph is the reciprocal of the original y-intercept. So if the y-intercept is at 4, the reciprocal is a quarter. If the y-intercept is at -7, the reciprocal becomes -1/7. Points where y equals 2 become 1/2. So I can take the reciprocal of certain points on the graph to help me find that out. So let's look at this page. The graph of y equals f of x is shown. You're not given the equation of this graph. You're told that it has an x-intercept at 2 and a y-intercept at 3. So if we use the suggestions on the previous page to sketch the reciprocal, what would we do? Well, the first thing that we start off with is that vertical asymptote. Where the 0 is, we draw in a dotted line. That's what we're going to start off with. And we draw it as a dotted line just so that we're aware that it's not actually part of the graph. Okay? That was the first step that we were to do. The second step said mark the invariant points. So they've drawn the lines y equals 1 and -1. It does not, -1 does not intersect the graph, so it's not going to have invariant points down here. But it will have invariant points here and here. Okay? The next thing that we're told to do, or that was suggested, is draw in our y-intercept of the reciprocal. So I look at the y-intercept of the original, which was at 3, because that's what it tells me. So the reciprocal would be 1/3. So I take this down to 1/3. Okay? Then from there, what I can do is I can think about how certain points in the graph are going to become when I take their reciprocal. For example, this point right here that's at 2, the reciprocal of that would be 1/2. So this point is going to drop down to here, because that's the 1/2 point. And then this point right here, which is at 1/2, the reciprocal of that is going to become 2. If I imagine this to be something like a 1/5, what would the reciprocal of that be? 5. So the reciprocal of 1/5 would be 5, which is going to put my point up there. And what do you notice the general curvature of this? Do you see a general curve yet? So look at this point. This point is, let's say, at 4. What would the reciprocal be? 1/4. So it's going to come down to about there. And remember from the other observations, as the original graph gets larger, the reciprocal gets smaller. So it's going to approach the asymptote. As the original graph gets smaller, the reciprocal gets larger. So I'm going to get this curve that's going to go like this. Something like that. What I would look for if I was marking this is I would look to see that it went through the invariant point. The other points, if you're slightly off, I'm not going to make a big issue of it, but I'm looking that it goes through the invariant point. I kind of want the y-intercept to be approximately where it should, and that it's approaching the y-intercept, or sorry, the horizontal asymptote this way and the vertical asymptote that way. If I flip to the other side, I can do the same thing. If this is at 1/2, the reciprocal would be at 2. If this was like a 1/5, the reciprocal is going to be at a 5. If this is a 4, the reciprocal is a 1/4. So again, what am I going to have for a curvature? I'm going to get a line that gets very close to the vertical axis up here, and the vertical asymptote up here, and very close to the horizontal asymptote down here. And again, what I would look for is I would look to make sure that it was going through the invariant point and that it's approaching the asymptotes. Okay? So what's the y-intercept of my reciprocal function? You guys have already told me this. What's the original y-intercept? So what would the reciprocal be? 1/3. Okay? So then it says, given that the equation of f of x is 3/4 x minus 2 squared, what would be my reciprocal? What are you writing down, Rachel? Is it like 4 over x minus 2 squared? Where's the 3? On the bottom. So I take 3/4 and I flip it because it's a fraction, so I'm going to take the reciprocal of that fraction. And then the x minus 2 squared, I take the reciprocal of that, so it goes to the bottom. Good job. And then you can use a graphing calculator to verify it. Okay, so we have another one. So I'm going to give you a couple of minutes, and I want you to see if you can sketch the graph of the reciprocal. Last question. Okay, so if we were to sketch this, you should have an asymptote going here and going here. So I have those two asymptotes drawn in where the x-intercepts are. This looks like it's, like, I don't know, 1 7/8 or something like that. So 15/8 or something to that effect. The reciprocal of that is going to throw it down here. Then I can put in my lines of y equals +1 and -1. And what that will do is it allows me to get my invariant points. So I now have an invariant point here, 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 and here. Then if I look at this point, this was a 2, the reciprocal of which is going to be half. So I'm going to get this part here, which is getting closer to 0. The reciprocal of that is going to get very large. So my graph is going to start to look like this. That's going to be the inside part. Then this section here from the asymptote this way, remember, as this gets large, the reciprocal gets small, and as this gets small, the reciprocal gets large. So the line would go like that, and then the same thing in through here, like this. So that's something like what my graph would look like. So the equations of the asymptotes, x equals -2 and x would equal +1. And the point a and 1/2 lies on the graph of the reciprocal. What's the value of a? So I look at where is the graph equal to 1/2 on the reciprocal. That's right here. So what was my a value? So if a, lies on the graph of the reciprocal, state the value of a. So if this lies on this graph, that means that a and 2 would be on the original. So if I put that into the coordinates of the vertex, I'll pause this for a second. So I had 1/2 in the wrong place. This is where my a equals 1/2 is right, or my y equals 1/2 was right here, the vertex. So the x coordinate of the vertex is what you're looking for. And to find the x coordinate of that vertex, it would be -2 + 1 over 2. Which would end up giving you -1/2. So the way that I find that vertex is the vertex is halfway between my two x-intercepts. That's where the -2 and the 1 come from. So -2 + 1 is the two x-intercepts, and the vertex is halfway in between. Okay? Okay, so we'll finish up the last question tomorrow, and then I'll give you the questions to work on for the class. So if we take a look at class example number 3, this one's a little bit different from the previous two, because it starts off by saying the graph of g of x, which is equal to 1 over f of x, is shown. What this means is this is the reciprocal function. Okay? The maximum point of g of x is at -3 and 2, and the y-intercept is at 1/5. Given that f of x is a quadratic, so what does a quadratic look like? It's that parabola. Sketch the graph of f of x on the grid and state the coordinates of the minimum point. So if we go back to the information that we're given, the maximum point of g of x is at -3 and 2. That's right here. That's the maximum. So if I think of this, if the reciprocal is at -3 and 2, the original would have the same x, but the y is actually going to end up being the reciprocal of the reciprocal. So the reciprocal of 2 is 1/2. Because again, if I apply my reciprocal to this function, I get 1/2 to 2. So that becomes my new point. Okay? The next point that I'm given is that the y-intercept is 1/5. So if the reciprocal y-intercept is 1/5, the original y-intercept would be what? It would be the reciprocal of the 1/5, which would make it 5. So that means that point is going to be right here. The other piece of information that we're given is that this is a quadratic, which means it has that parabola shape, either up or down. But from here, we can conclude that this must go up. And again, thinking about what we know. If the reciprocal approaches 0, the original had to approach infinity. So that means that my graph would look like this, and then like this. So the last part says the graph can be written, so this is y equals f of x, this is my original function, can be written in that quadratic, in that standard form of y equals a times x minus p squared plus q. So we need to determine the values of a, p, and q. So if we go back to what we know, what are p and q? It's the vertex. So what is the vertex in my graph? It was this point right here, which was my negative 3 and 1/2. So negative 3 and 1/2. So in my equation, I would have y equals a times x minus negative 3, which would be x plus 3 squared plus 1/2. Now I need to solve for a. So to solve for a, what I want is I want to know an x and a y value that's on the graph. Well, I have that right here. I have the y-intercept equals 5, so I have a point on the graph that's at 0 and 5. So I can substitute that into the equation. Y equals 5, x equals 0, so I have 3 squared. 3 squared would be 9, so I have 9a plus 1/2. So then to go through and continue solving this, I might find it easier at this point in time if I change that 1/2 to a 0.5, subtract by 0.5 on each side, and I get that 4.5 equals 9 times a, divide both sides by 9, and I get 0.5 or 1/2. So then my final equation would be to take the value of a and p and q and put it all together. So I get y equals 1/2 times x plus 3 squared plus 1/2. So the questions that I would like you to work on are questions 1a, 2b,